AE1601 glider project by Group 19, Swayam and Isabel. Purpose. The purpose of this experiment was to build, design and test a hand-thrown glider using basic materials, applying principles of aerodynamics and engineering. Through this project, we aim to explore how design decisions such as wing shape, tail configuration and material selection affect flight performance. By integrating on our initial designs and testing their performance, we gain hands-on experience in the engineering design process while reinforcing theoretical concepts learned in class. These are the requirements of the project. A summary of them include producing a glider primarily made of balsa wood that fits in a 16 by 16 square that is able to fly in a straight horizontal distance of 20 feet without the use of any automatic control. Other requirements also include sketches. Measure of success, vehicle construction. The glider fits within a 16 by 16 square without disassembly. The glider remained intact during flight and didn't lose any parts. The performance, the glider achieved the forward flight distance of 21 feet, recorded officially, and 32 feet as the maximum horizontal on the day of the official glider test. Design and testing. The glider is balanced with the center of gravity near the quarter chord of the wing after the iteration. Alternative generation. First alternative is the adhesive. The adhesives were a crucial consideration for assembling our project. The three adhesive options were evaluated were super glue or hot glue gun and orange elastic tape. The hot glue gun, the pros of this were the hot glue gun provided excellent stability as it hardened into a solid structure, which efficiently secured the attached parts. The cons of this was it may disrupt weight distribution due to its density and the drying process is time consuming. The super glue, the pro was super glue maintains a consistent weight distribution and offers high strength, holding materials firmly together. The con is it does not contribute much structural support. Under impact, the materials, e.g. the balsa wood, would bend or fracture due to insufficient flexibility. Orange elastic tape. The pros of this was the tape is quick and easy to apply. It provides considerable strength and support when attaching components. The cons of this were that the tape's strong tension may stress the balsa wood, pulling it inward and potentially causing cracks. The second alternative was the wing shape. Wing shape was another crucial design consideration. Our research explored various wing geometries, particularly elliptical and rectangular wings. For the elliptical wings, according to partsbase.com, elliptical wings are considered the most efficient and aerodynamic due to the curvature, which minimizes drag and ensures optimal lift distribution. However, their curved structure makes them difficult to manufacture, whereas for the rectangular wings, in contrast, were easier to produce because of their simple straight line construction. However, they were less aerodynamic and do not perform as well in terms of drag reduction and lift efficiency. Given our machining reinforces, we opted for elliptical wings to take advantage of the superior aerodynamics and reduced drag. The third alternative was the dihedral versus no dihedral. We considered implementing a dihedral wing design, but ultimately chose a non-dihedral configuration. The dihedral wings offered increased stability during the flight, and the con of this was even though they increased stability, they increased drag too, which would hinder our goal for maximizing glider distance. Moreover, their complex geometry would have posed manufacturing challenges. For the non-dihedral wings, these wings generated less drag, allowing for greater flight distance, albeit to the cost of reduced stability. Given our primary goal, the non-dihedral wings were the better choice. Alternatives with highest possibility of success. So the adhesive, based on physics Foru's findings, hot glue is a viable option due to its strength, provided we were quick to position components before it hardens. The wing shape, research supports that elliptical wing shape as the optimal choice for reduced drag and improved efficiency. And dihedral versus no dihedral or non-dihedral configuration aligns with our objective to minimize drag and maximize flight distance. Initial concept. The initial set of design choices were made up of two rationales: the probability of success determined in the design phase and making it. That is why we decided to give it a try to the rectangular wings in our initial design. For the sizing, for the wing dimensions, we researched effective wingspans and chords for gliders, prioritizing design that maximized lift, and the elliptical wing shape was the best, which we selected for a final, with a wingspan of 15 inches to stay within the 16-inch constraint and a chord length that ensured sufficient lift and stability. The fuselage length was sized at 12 inches to provide a stable platform for mounting the wings and tail while balancing overall weight and aerodynamic efficiency. The tail dimensions, the horizontal tail span was designed to be 4 inches with a chord of 2 inches to maintain stability without adding excessive drag. The vertical stabilizer was sized at 2 inches. Weight distribution, we reduced mass by carefully sanding down the balsa wood while increasing aerodynamics. And for the wing placement, we placed the wing slightly further back in order to increase the lift and stability. Testing evaluation of stability. The glider flew smoothly with one small swing that didn't significantly affect its performance. The spin was minor and didn't cause any major instability, so the overall flight path remained stable. However, we believe that slight adjustments could help eliminate the spin and make the flight even more predictable. Testing. The evaluation of initial performance against requirements. The glider successfully met the 20-foot requirement, flying a total of 31 feet. However, it landed nose first, which suggested that the center of gravity might have been too far forward. The clay attached at the tip was likely contributing to this. So we planned to adjust the amount of clay or move it closer to the body to improve the weight distribution. By making these adjustments and testing again, we expected to achieve a smoother glide and refine the landing stability while maintaining the impressive 31-foot distance. Design alternatives, the adhesive, super glue, hot glue, orange elastic, adhesive and super glue with tape. So we decided to use the super glue. Was useful for the first design but caused the wings to break easily upon impact. The second design used orange elastic adhesive, while the third one used hot glue, but it was really too heavy. So for the final design we combined super glue with tape, reinforcing the wings to prevent breakage while maintaining lightness and aerodynamics. So the final decision was using super glue with tape was chosen for the final design as it balanced durability, weight and aerodynamic performance. The second alternative was the wing shape. We tried out the rectangular and then we tried out the elliptical in order to see which one was better, and we concluded that the elliptical was better as it was more efficient, providing the longer and more stable flights. The third alternative was the vertical stabilizer length, and for that we used short stabilizers, reducing drag, but it compromised directional control, whereas the longer stabilizers improved control but increased drag. So we chose a medium stabilizer in order to get both sides equally. Mass reduction, we tried to reduce the mass as much as possible by sanding it down and to get better aerodynamics. And the wing distance from the nose, we put the wings slightly towards the middle compared to at the front of the plane or at the back of the plane in order to obtain the best lift. This is the image of the final plane and the image of the center of the gravity. Using data, I then calculated the lift coefficient, which came to 0.137, and then using that I was able to calculate the drag coefficient, which came to 0.012. The calculations are shown in a step-to-step process of how exactly I found it. This is a video of our glider during the official glider fly off day, which made the flew a distance of 32 feet. On the left-hand side of the PowerPoint presentation, we have an image of our glider in a 16 by 16 cutout, which meets with the requirements. And on the right-hand side, we have a video of our best flight of our glider, which flew a total distance of 52 feet. In summary, our glider project involved several iterations and adjustments to meet the design requirements. We started with different adhesives, wing shapes, stabilized lengths, and mass distribution strategies to improve performance. Through testing, we managed to achieve a flight distance of 31 feet and a maximum flight distance of 52 feet, surpassing the 20-foot requirement, though we still faced challenges with the nose first landing during the beginning. Our final design involved using super glue combined with tape for better wing stability, elliptical wings for involved aerodynamics, and adjusting the center of gravity with carefully placed clay. These choices led to a glider that was stable, flew a good distance, and met the project's objectives. Looking back, we would focus more on fine-tuning the weight distribution earlier in the process to avoid the nose first landing. Additionally, to improve stability and control, we would add more horizontal stabilizers to the rear by increasing the height of the tail, the fin, and possibly adding another horizontal layer on top of the tail fin, or incorporating additional tail fins on either side of the main one. However, we are pleased with the progress and the lessons learned about design iteration, problem solving, and testing. If we had to do it again, we would refine our approach to achieve an even smoother flight path and more stable landing. These are the sources we used in order to obtain the best glider possible. Thank you.